Greetings to all participants and organizers of the International Conference on Nonlinear Science and Complexity. My name is Suarez, Ogando, and I am a student at the Faculty of Chemistry of the University of Havana. And I will be presenting the work Ferroptosis as a biological phase transition for chronotherapy of epithelial-mesenchymal transition of the tumor growth. It is known the existence of different types of cancer and their incidence in the world population, and the forecasts based on mathematical models point to an increase of approximately 11 million of new cases reported by 2040. Hence, the need to study the dynamic and evolution of the disease with the aim of drawing up effective strategies that allow obtaining better therapeutic results. One of the alternatives that make possible to improve the effectiveness of anti-cancer therapies and reduce the toxicity of the drugs is chronotherapy. Chronotherapy is based on the synchronization of the body's circadian rhythms with the application time of the therapy. Now, the evolution of the disease can be understood through three fundamental states. The vascular state corresponds when the tumor is microscopic and can be detected by conventional techniques. The vascular phase occurs after the angiogenesis process, and at this stage the tumor has dimensions that make it detectable and where it has the capacity to invade other organs, known as the metastatic stage. During this evolution, the epithelial-mesenchymal transition mechanisms can take place, and this process has been linked to the initiation of the metastatic process. This epithelial-mesenchymal transition mechanism is a biological process where the epithelial cells undergo a phenotypic change and acquire mesenchymal characteristics. The process is characterized by the loss of cell-cell contact, and the resulting mesenchymal cells have a greater mobility and a greater capacity to evade the apoptosis process and immune response, resulting in a greater pharmacological resistance to therapies. Related with this pharmacological resistance of cancer cells is the emergence of a new type of regulator cell death known as ferroptosis. This process is characterized by the accumulation of reactive oxygen species in the intracellular medium, and the interesting point here is that the induction of the ferroptosis process in cancer cells make possible to overcome the pharmacological resistance displayed by several tumor lines, hence the growing interest in the designs of new drugs and therapies based on this process. In previous work, we developed a model where the main steps of the ferroptosis process are related to the vascular and vascular tumor growth process, and the epithelial mesenchymal transition steps is also included. From the model, it was obtained that a variation in the concentration of oxidative puffer fragment taken as the control parameter lead to a variation in the dynamic of the system, as can be observed in the bifurcation diagram, where a chaotic behavior is reflected for low values of the control parameter. Therefore, the main goal of this work is to develop a model that simulates the application of a chronomodulated treatment based on triggering the ferroptosis process in cancer cells, and from this, identify the optimal values of the dose and application frequency of the therapy. With the objective of simulating the application of a chronomodulated treatment, a periodic perturbation was introduced to the model shown previously. This perturbation function represents the action of applying a drug with the objective of increase the concentration of the oxidative puffer fragment, because these constitute the effectors of cell death due to ferroptosis. In the perturbation function, the parameter A represents the amplitude of the dose of the drug, while WP represents the frequency of application of the drug. From this model, it is obtained the non-autonomous system of ordinary differential equation shown on the slide, which allows representing the dynamic of the system. Now, in order to analyze the optimal condition to apply the therapy in terms of dosage and appropriate application times, the bifurcation diagram shown on the slide was constructed. In this bifurcation diagram is evaluated the variation in the dynamic of the system as the amplitude of the dose and the frequency of application of the drug are changed at the same time. The bifurcation diagram shows the existence of large areas of periodicity 1, 2, or 3 where the system exhibits less complexity and therefore the disease offers less resistance to treatment in the case of combined therapies. It's observed that the areas of lower complexity are mainly concentrated for high values of the amplitude of the dose. However, it's observed that by modulating the frequency, it's possible to obtain a large area of lower complexity for low values of the dose, even finding zones of period 1. These areas of lower complexity are mainly concentrated for high application frequency values, and in this way, it's possible to reduce the side effects linked to high doses of the drugs by changing the frequency of application. Now, with the objective of studying the behavior of cancer cell population following the application of a therapy, the average concentration of each cell population was obtained for the different values of the amplitude of the dose and application frequency. The graph shows the average concentration of the mesenchymal cell population for different values of the control parameter, and the green dashed line shows the values of the average concentration of the mesenchymal cell population for the Sternberg system in order to evaluate the behavior of this population before and after applying the therapy. In this way, it's obtained that after the application of therapy, there is a reduction in the average concentration of the mesenchymal cells for most of the values of parameter evaluated, obtaining better results for high values of the dose. While in the case of epithelial cell population, the behavior is different. In the case of avascular cells, is observed an increase in the average concentration after the application of the drugs for all values of frequency and dose. On the other hand, in the case of vascular cell population, it is observed that only for certain values of frequency and dose it's possible to achieve a decrease with respect to their initial value pointed with the green dashed line. This behavior has been identified experimentally, and the explanation here is based on the fact that ferroptosis process trigger an inflammatory response due to the damage of healthy cells, and this response has been linked to the process of initiation and development of cancer, hence the preferential increase in the population of avascular cells. Now, in order to evaluate the result obtained in our model with available experimental results, the following graph of an in vitro experiment is shown. The graph shows the behavior of the mesenchymal and epithelial cancer cell population after the application of the drug that induced the ferroptosis process. The graph shows that after the induction of ferroptosis, a decrease in the number of mesenchymal cells is achieved, while the epithelial cell population show a tendency to increase, as was predicted by our model. In this way, we can conclude that the use of a chronomodulated therapy based on triggering the ferroptosis process in cancer cells made possible to reduce the robustness of the disease, and controlling the frequency of application of the therapy will enable a decrease in toxicity while achieving a decrease in the robustness of the disease. And as a last point, we can say that the mesenchymal cells have the greatest susceptibility to the ferroptosis process, while to achieve the decrease in the epithelial cell population, it's necessary to effectively control the amplitude of the dose and the application frequency of the therapy. As a future perspective for this work is to analyze the combination of therapeutic targets in the model with the aim of generating new treatment avenues. Well, that's all I want to share of this work, and I would like to thank all of you for your attention. Thank you very much.